Good morning, Chemistry 12. Hopefully you folks are well rested. Today's lesson is on electrolytic cells. Now, electrolytic cells are basically the reverse of electrochemical cells. Now, I'm just going to share the screen here. Now, electrochemical cells, you folks had done last day, from the last day here. And what it was, you have the notes here, is where you have a chemical reaction that produces electricity. Electrolytic cells is actually the reverse, where you take electricity to generate a chemical reaction. You could think of it like recharging your battery. When you're recharging your battery, you're adding electricity to regenerate some of the chemicals. Okay, so I want to go through that today. And so electrolytic cells. Now, you have these in your notes. So electrolytic cell is a process where an external source of electricity, okay, so what we have here is an external source of electricity is required to cause a redox reaction. That is electrolytic cell. Okay, electrochemical cell was a redox reaction, produced electricity. Electrolytic is where you have electricity producing a redox reaction. Now, what I have down here is a sort of a breakdown of the difference between the two. So you have electrochemical cell and you have electrolytic cell. Now, the key difference is here in the first step. Notice, this is key, notice the difference between the two. One, you produce energy, the other is energy is required. So for electrochemical cells, you produce electricity or energy. Electrolytic is you require energy. Now, if you look at bullets numbers 2 and 3, you still have an anode and you have a cathode just in both chemical reactions. You have an anode, you have a cathode. Now, there's this different list, but the key one you need to realize is that anode, there's oxidation, cathode is reduction. Here, the anode, there is oxidation, cathode, there is reduction. Now, all the other bullets under those categories are secondary, okay? In terms of how do you obtain oxidation and what are the results, those are all different depending on the electrolytic or electrochemical cell, okay? But the key thing is anode is always oxidation, cathode is always reduction. Now, the other thing is this. Notice here, there's only one type of cell, and here there are 3 types of cells. Now, what do I mean by this? You might say, well, Mr. Chan, last day's notes, if we change the different chemicals, wouldn't we get multiple different cells? But the thing is this, if we look at the diagram that's right here, it doesn't matter what chemicals we use. In this case, we had zinc and copper. We could change it to something else, but the setup is exactly the same. We have a salt bridge, we have 1/2 reaction, 1/2 reaction, and we generate electricity. The only difference is how much electricity we produce. When we talk about electrolytic cells, there are 3 different types of setups that will give us 3 totally different products, okay? So what I want to do today is I want to go over 2 of them today for us to talk about, okay? So what I want to do is I want to take a look at 2 types of cells. So the first one is called a type 1 cell. Now, this is the simplest cell, and it is two inert electrodes. So what is inert? Inert basically means that it does not react with anything. It does not react. Okay? And in a molten binary salt, so in a molten or liquid binary salt, okay? Binary means, remember, two elements. Now, for example here, let's look at sodium chloride L. No, notice the phase symbol is L. This means that it is liquid or melted. Okay, please make sure you note the difference between liquid or melted versus solution. Example would be if we took a look at sodium chloride, melted would be if we just took our table salt and we heated it to like 5,000 degrees Celsius, and what we get is we get liquid. What you put in, let's say, your food, that would be salt solution. Okay, that would be AQ. Now, how does it look? So this would be a electrolytic cell. So notice a couple of key things here. Okay, so notice the first thing is that there's a battery. The battery gives energy. Okay, and right now what we have is we have two electrodes. One is connected to the positive end of the battery, which is the anode, and one that is connected to the negative end of the battery called the cathode. Okay, now an easy way to remember it is whichever one is connected to the negative end of the battery, we just put it with a bunch of negatives. And whenever we find out which one is a bunch of negatives, the other one by default must be positive. Okay? Now, so when you melt a salt, what you have is you have ions. Now notice the chlorine ions is attracted to the positive electrode. Sodium ions are attracted to the negative electrode. Now you might say, why? Easy. In this case, movement, we move by electrostatics. What do I mean by electrostatics? Means opposites attract, like repels. So in this case, the sodium plus 1 is attracted to all the negatives, and the excuse me, and I did sneeze in my elbow. And the chlorine minus 1 is attracted to all the positives. Okay? Now, so because the sodium is attracted to the negative, it has to undergo reduction. It has no choice because there's electrons, and so what you get is you get sodium solid. Because the chlorine is attracted to the positive end, it has no choice but to give up electrons. Okay? So what happens is that these reactions have no choice. They are forced to give up, to give or gain due to attraction. Okay? So in this case, Chlorine is forced to give up electrons. Sodium is forced to accept electrons. And when we combine the anode and the cathode reaction, what you get is you get this overall reaction. And voltage. Now, notice when you read this, what are you producing? In this case, the sodium gains mass because you're producing solid. Okay, so what you would get is here you would get sodium solid. Because that's what's produced. And chlorine, what happens is you produce a gas. Okay, the anode doesn't lose any mass because chlorine gas is formed. So what you get is on this side is you get little bubbles of chlorine gas. Okay? Now, this goes back up to here. If we look at electrolytic cells, notice we said, oh, may lose mass, may gain mass. Okay? It all depends on the product. Okay? Now, notice here, it gets minus 4.07 volts. You might say, well, Mr. Chan, how did you get that? Well, it goes back to, if we look at our standard reduction potential table, what we do is we look at sodium undergoing reduction, okay? Sodium undergoing reduction, which is minus 2.71. And we have chlorine undergoing oxidation, which is 1.36. Now, since it is undergoing oxidation, remember we have to flip the sign of chlorine to minus 1.36, and we combine it with the sodium, and this is how you get a voltage of 4.07 volts. And so basically, for the reaction to occur, the cell needs to operate at 4.07 volts. Okay, so we need anything above 4.07 volts to make this reaction work. Okay, that is a type 1 cell. Now, type 2 cells. Here's the key difference. The ions dissolve in solution. The key word here is solution. Okay? So we have to consider water may oxidize or reduce as well. Now, what do I mean by the difference here? Let's say we have CuSO4, but notice the phase symbol. This is AQ. You notice this. Now, another way you can say it's a solution is like a 1 molarity CuSO4. So in this case, it's a solution. You have to consider water. Now, again, the setup is the same. I'm just going to wipe out the current here. Okay? So what you have is you have one side is the negative. So I'm just going to draw the negative here. And in this side, we have the positives because it's connected to the positive end of the battery. Now, again, by electrostatics, notice the direction of the copper ions and the sulfate ions. Here, you have the positive ions, which represent copper, moving over to the negative charged cathode. And you have the anions, which is the negative ions moving to the positive anode. Now, In this case, we have to think water can actually do both. It is attracted to the negative and the positive. Why is water attracted to both? It goes back to the polarity of water, where water has a partial positive, partial negative end. So what happens is this. In the anode, so at the positive end here, okay, what you have is you not only have SO4 undergoing oxidation, you also have water undergoing oxidation as well. At the cathode, what happens is you have copper undergoing reduction and you have water undergoing reduction as well. So you might say, which one? Will undergo oxidation? Also, which one will undergo reduction? Okay. Now, so what do we need to do is same thing. We need to look at the standard reduction potential table. Okay. Now, at the anode, notice both the water and H2O can oxidize. But since H2O is a stronger reducing agent, it will tend to oxidize more readily than SO4. Now, what do I mean by this? So if we look at our standard reduction potential tables, okay, what we do is we look for undergoing oxidation, which is the right-hand side. Okay, so we're looking for our reducing agents. Remember, that is undergoing oxidation. Oxidation. So we have SO4 up here, and we have water down here. We're just focused on the right-hand side. Now, notice, since water is further down on the right-hand side, this is stronger than SO4 minus 2. Okay? So this is why we have here, that's why we said H2O is stronger. So this, yay, this is the preferred reaction. Now, we do the same thing on the right-hand side. I'm talking about reduction, where we look at copper. Copper 2 plus and water can reduce, but copper 2 plus is a stronger oxidizing agent, so it'll reduce more easily than water. Again, what do? We take a look in this case on the left-hand side. This is undergoing reduction. Yeah, come on, there you go. This is undergoing reduction. We're looking at on the left-hand side. So we look for copper 2 plus. Where's copper 2 plus? I have no idea. There it is. We have copper 2 plus, and we have water. Okay, so again, if you take a look at the standard reduction potential table, since copper is higher up than water, in this case, copper 2 plus is stronger. Again, location, 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 location. Okay? And so here, this one is the preferred reaction. And so the preferred reaction will be between the strongest oxidizing and reducing agents. Okay, so in this case, we know that, oopsie, it's not here. Whoopsie, whoopsie, whoopsie. This one would be copper. It's up here. So we know for the oxidation, it's water. We know for the reduction, it is copper. And this is what we would get as our overall reaction. Okay, so if we were to take a look back here, what would you produce in terms of your electrolytic cells? What you would get is you would get oxygen as a product. At the, in this case, at the anode, so you would get gas bubbles, and here you would get copper at the cathode. So what you would get is you would actually get copper solid. Okay. Now, here's an easy way you can think about it, and I use this as an example. All right. In this case, type 1 is simplest. There is no doubt of which one goes to the anode, which one goes to the cathode. The example I give would be like, a married couple with no children. If one wants to have, Cactus Club, and the other has, wants, let's say sushi, you know what? If they don't like it, they just go their separate ways and they have their separate dinners and come back together. Okay? In this case, when you think about it, again, it's Cactus Club and sushi. But now what you also have to consider is water would be like your child. What does the child want? Does the child want Cactus Club, or does your child want sushi? And they will go with that particular parent to get the food. Let's say you're at the food court or something like that. I don't know. Okay, so water would be another consideration, okay, that you have to consider to undergo oxidation and reduction. Okay. All right. What I'm going to do is I'm going to stop here. Okay, and I'm going to give you some examples. All right. Next day, I am going to talk about something called this this overpotential effect, as well as the type 3 cells. All right, ladies and gentlemen. So that will be it. So what I want you to do is I want you to definitely try and practice, because there's going to be lead up to your next lesson. All right, ladies and gentlemen.